Hello, in this last video screencast about LUG, topic 6.2, we're going to talk about a couple other examples, look at some problems together. There are some classics in here. All right, so here's some ways we can apply these ideas. This is a type of problem that the IB absolutely loves to give you. It's a ratio problem, I call them. They love to do comparisons where you use the equation for gravitational field strength or gravitational force. So here it is. We got a magnitude of a field strength at the surface of some random planet that's got a mass m and a radius r, and the field is g strong. And then they say, what is the magnitude of gravitational field strength on the surface of a planet that's got 4 times the mass and 3 times the radius of the other one? There's no numbers here, which freaks some students out. You don't like this because there's no numbers to plug in. You have to do it all with algebra. Essentially, what you want to do is use the LUG equation, the gravitational field strength equation, rather, because we're talking about the mass of an object and the radius of an object. And I know at the surface of a planet, I can plug in the radius of an object for little r squared. That'll tell me how strong the field is at the surface, if you remember doing that example for the Earth. Okay, of course, we have no numbers here. If you're feeling mathy, and as you practice this more, you might get to a point where you can kind of do this and think about these relationships. Think about these math relationships. If you have a good math sense, you can kind of look at this equation and say, okay, well, what happens if I have another planet and I quadruple m and triple r? Well, making the mass bigger would make g bigger. Making r bigger would make g smaller. And this is like a squared relationship. All right, the answer is going to be 4/9 g. If you can see that already, amazing work. But that takes some practice often. So I'm going to show you a method that will always get you there. This is more time consuming, but it'll get you to the same place, and it's a good way to visualize what we're doing. So essentially, you want to use this equation twice. Whenever you have a ratio problem like this, use this equation twice, and then we're going to divide them to compare. So G1, I'm going to call it for this first object. I'm going to multiply gravitational constant times the mass of that object, which is just m, and the radius, because that's how far away we are from its center, big R. That's g. What I want is to figure out how big the new g is in comparison. And so I'm going to use the same equation, g times m over r squared. But now my mass creating the field is 4m. And the distance to the distance to the center of that object from the surface is 3 times big R. So this is how I apply that equation for the second object. And notice I'll get this, g times 4m over 9r squared, because the radius is squared, so 3r, the whole thing gets squared. So 3 gets squared. The first planet has a field strength this big. The second planet has a field strength this big. All right, at this stage, you might kind of see that this is 4/9 the size of the other one, but we can solidify that with this. Here's what you can always do. I want to compare G2 to G1, so I'm going to write them as a ratio. G2 over G1. What is the comparison here? This is the move. All right, if you need to compare two things like this, use the equation twice, put the new one on top, divide it by the old one, and see what you get, because this might look like a lot of nonsense right now. But here's the beautiful thing. I got a big G on top. I got a big G on bottom. I got a big M on top, big M on bottom. Big R squared on top, big R squared on bottom. All that stuff will cancel out. Yeah. Everything that's not your factor that you've changed by cancels out. And what we see is G2 over G1. The ratio G2 to G1 is 4/9. In other words, I could solve for my new gravitational field strength, and it's 4/9 of G. I suppose we should officially call that 4/9 of G based on the way the problem is based. But there you go. That ratio method will always work for you. Again, whatever equation you're using, these ratio problems will come up in a lot of different contexts, not just with field strength. So for this case, we're talking about field strength. Take the equation for field strength, use it twice, once for the new situation, once for the old situation. Divide new situation by old situation, cancel everything out that cancels out all your variables, and see what you're left with. You can then multiply by the old thing to really make it clear, and make sure you answer the question. Sometimes they'll ask for one versus the other, but our new field has got to be 4/9 the size of the other one. And again, we can kind of think through and check and make sure that makes sense. I know that this is going to increase the field strength compared to the old one, but this will decrease the field strength. And because there's like an R squared, it makes sense to me that would have a bigger impact. And so I end up with a weaker field at this new planet, even though it's much more massive. It's way bigger, and I'm way further away from the center. So I end up 0.49. It's a little less than half the field strength on this new planet. Right? Again, they love problems like this. You can compare like how strong the gravitational field is on Jupiter compared to Mars, compared to Venus, compared to Earth, and so on with this kind of method. There you go. You'll practice a lot of these. They're great. And here's one more, two more really practice problems when we have multiple things creating fields. Because of course, every object with mass creates a field. Gravitational field is a vector. The field strength is a vector. Its direction tells us which way a force would act. So remember, the gravitational field around the Earth points towards the Earth. The moon, though, also has a gravitational field that points towards the moon. And so you might ask the question, what happens if you go out into space and you're halfway between the Earth and the moon? The Earth is pulling you one way, the moon is pulling you the other way. We're going to calculate field strength twice and add them as vectors. This is just like doing a net force or any other vector addition that we do. So the first one is a classic one that the IB would love to give you. Find the resultant field strength between two objects, some point in between them. Typically, they'll only do this in a straight line, which is nice. You're not often going to have to deal with angles in this kind of situation. So we're just on a straight line right in between the Earth and the moon. So the Earth has a field one way, the moon has a field the other way. So you try these. You try the example problem here. See if you can figure out how strong the field is right between the Earth and the moon. Make a sketch. Picture your two vectors contributing and think about how you want to add those together. And then if you're feeling strong, there's a more fun problem where there is a point in between the Earth and the moon where there is zero gravitational field strength. There is a point where you could experience true weightlessness if you were just at the right spot. See if you can figure out where that might be. All right, pause the video, try one or both of those. All right, great job. Here's how to do these. So here's that first example, finding a point right in between the Earth and the moon. So here's my Earth, here's my moon, here's a point smack in the middle. What that means is I'm equidistant from the Earth and the moon, so I could call the distance between the two of them both r, or whatever you want. The idea is, at this point, there's a gravitational field from the Earth pointing towards the Earth. The Earth is trying to pull me that way. And there's a gravitational field from the moon pulling me towards the moon. These two fields, I can find their size with the equation for field strength. And all I'm going to do is subtract them because they're vectors. One's going this way, one's going that way. So one's positive, one's negative. And I'm just looking for the magnitude, so I'm just essentially going to subtract them from each other. Okay. Let's do this then. I'm going to do field of the Earth minus field strength of the moon to find the resultant field strength. I drew it this way, so my answer will officially be to the left because I'm imagining this is going to be bigger because I know the Earth is bigger than the moon. All right, we're really solving for magnitude here. Okay, so I've plugged in my equation. G times mass of the object divided by distance of the object squared tells me how strong the field is at that point. Same thing over here. If I want to be math fancy, I can factor out my G over R squared because they're the same. I'll save myself a little bit of calculator work, and here we go. There's the mass of the Earth, there's the mass of the moon, and what I need to do for R is take the distance between the Earth and the moon. That's that lunar distance we did in an earlier video. So you do need that or need to look that up if you don't have it in your notes from before. But we'll take that distance between the Earth and the moon, divide it by 2, and that's the distance from the point to each object creating the field. All right, make sure you put it in meters. And what we find is this, 0.011 newtons per kilogram. Very weak, mostly because we're far away from both the Earth and the moon. All right, so that's what you get when I find the resultant field strength, 0.011 newtons per kilogram. And if I want to talk about the direction, it should be towards the Earth because this one is going to be bigger. But towards the Earth, so whichever, wherever you happen to be between the Earth and the moon, the field is directed towards the Earth. All right, so that's that one. If you haven't already, try the second one now with that same kind of idea. Can you figure out where the field strength is 0? Okay, here's the solution to that one. This one's more exciting. It's a system of equations you have to set up. And so there's some point, probably, see if you can convince yourself that this point will have to be very close to the moon because it's got less mass. There's some point in between the Earth and the moon where the field from the moon and the field from the Earth must be the same size, but in opposite directions. So that's how I'm going to start. The magnitude of the Earth's gravitational field is equal to the magnitude of the moon's gravitational field. Since one's pulling me one way and one's pulling me the other way, the total will be 0. So I can set these equal. If I do it this way, the g's cancel out, and I end up with some kind of ratio stuff. So I'm kind of ratioing here, because here's one way to do it. Essentially, there's a lot of ways to do it. But if we know the mass of the Earth and the mass of the Moon, I have 2 unknowns. I'm going to later need a system of equations, and here's what my system's going to work out to be. This is my other equation once we get there. All right, but so one thing I can find from LUG, well, the G field strength version of LUG, is that the ratio of the distance to the Earth and the distance to the Moon, I got to square root my mass ratio. And plug in, I end up with something like 9. So I need to be 9 times closer to the Moon than the Earth. Something like that. My distance to the Earth is 9 times the distance to the Moon. That's what this one kind of gets me to. I do know the distance between the Earth and the Moon, so I know this total distance. And the other part of this system is that the distance to the Earth plus the distance to the Moon have to add to that distance. So I'm calling it D equals the R to the Earth, my radial distance to the Earth, plus my radial distance to the Moon. And now I'm going to substitute in. So I'm doing a system of equations. There's my first equation. There's my second equation. You can, of course, solve these in different orders. You could substitute in up here and have some other exciting math that happens. But one way or another, the exciting math you get should give you this. You got to be about 38,000 kilometers away from the Moon and about 346,000 kilometers away from the Earth. And at that point, close to the Moon, you would indeed feel 0 total gravitational force, 0 total gravitational field strength. All right, so there you go. There's a couple of the more exciting applications of how to use these equations. Lots of more practice coming your way that will look pretty similar to this. And that's everything you need for a LUG, so have fun.